Hello everyone, and thank you once again for tuning into my video. First, I just want to say that I believe going forward, weather forecasters will be looking at those particular days where we have a double period to forecast any future snowstorms. Second, I just want to say that this two-dimensional motion that I'm going to go over with you guys is going to require two different videos. So after viewing this one here, please look for my second video. And finally, there is a possibility of no school even tomorrow, or delayed opening or whatnot, or I might not see you. So I will be posting the take-home assignment for the Parametric Equations unit on Moodle, and it'll be due when you come back from the break. As I said in class, you will be allowed to talk to one other person to help out with this particular test. You are responsible for handing in your own assessment, but I will allow you one person to talk with to help out with completing your test. So just look out for that on Moodle. If you recall, in our last lesson, I introduced parametric equations by expressing the desire to analyze two-dimensional motion in the xy plane, because a single equation isn't sufficient enough to be able to capture this motion, so thus the need for parametric equations. However, another thing that we're going to need to analyze our two-dimensional motion are vectors. Now, everyone has seen vectors at some point. At least you've seen a vector in Algebra 2 Trig. And in Algebra 2 Trig, you analyze vectors. In particular, you analyze the resultant vector. But before we just move on, I'll just do a quick review of vectors so that you have the necessary background to perform the necessary calculations. If you look at the example that I've drawn here, literally all I've drawn out in the xy plane is the point AB. And as is, if you just have plotted this point in the xy plane, it literally is just a point. Now you may be sitting there saying to yourself, Mr. Ambrose, why in the heck am I listening to this video? I already know what a point is in the xy plane. But if we now take that same point AB in the xy plane, and I'm now going to draw an arrow that goes from the origin to that point AB, we now have the vector A, B. Now, you'll notice that when I wrote out the vector A, B, I didn't use the same soft parentheses that we use to express the point AB in the xy plane. Instead, I used a bracket that had a sharp edge to it. And so, to express any vector in calculus, and in particular here the vector AB, we'll use a sharp bracket to denote that that is indeed a vector. Now, vectors are very helpful because they show both a direction and a magnitude. In the example that I provided here, the direction of this particular vector would be that from the origin to the point AB, we are going up and to the right. And so any particular vector will always express a particular direction. The other thing that you can extract from a vector is some magnitude. Now, back in Algebra 2 Trig, you captured the magnitude when essentially you found the length of your resultant vector. And to do that, you essentially found the length of the diagonal in your parallelogram. So, since magnitude is really just the same thing as a length, or can be captured by a length, in the example that we have here, to find the magnitude of this vector A, B, we just had to find the length of that arrow. And to do that, since we're in the xy plane, we can just utilize our distance formula. So the distance formula is nothing other than the square root of well, it would be the change in our x value squared. And in this example here, the change in our x value would be just a. And then we add to that the change in our y value squared. And in this problem here, the change in our y value would be b squared. And so if you notice, the magnitude of this vector a comma b is nothing other than the square root of the sum of the squares of each of the components to our vector. Now that we have a background on vectors, we're now ready to perform our analysis of two-dimensional motion. And in that analysis, we're going to utilize both those vectors as well as parametric equations to look at similar things that we examined when we looked at one-dimensional motion. So, in particular, we analyzed two-dimensional motion using parametric equations, and we represent position, velocity, and acceleration as vectors to help with that analysis. In particular, position, which can be expressed as s of t, will equal the vector x of t, comma, y of t. And velocity, which can be expressed as v of t, will equal dx dt, comma, dy dt. And finally, acceleration, which you can express as a of t, will equal the second derivative of x with respect to t, comma, the second derivative of y with respect to t. Now, again, notice that each of the position, the velocity, and accelerations that we have here are all expressed as vectors, which means that each one of them has both an x component and a y component. Another thing to keep in mind is that the work that we did in the prior lesson, where we were finding things such as slope and whatnot, you must keep those things separate from the calculations we're going to do here. In particular, the dy dx and the second derivative that we calculated there are not at all used in this analysis of two-dimensional motion. So now I'm going to go through an example that will capture all the things you're responsible for being able to do with two-dimensional motion. And I also just want to remind you guys that on Tuesday, at the beginning of the lesson, I quickly went over with you all the things that in particular we did with one-dimensional motion. And so as I go through some of these calculations of two-dimensional motion, I may refer back to those particular notes there. So this example that we have here is that we have that the position of a particle is represented by the parametric equations x equals the cosine t and y equals the sine of t. And the first thing that we're going to do is to find the position, the velocity, and the acceleration vectors. Now, the position vector is going to be fairly simple. We already really have both the x and the y components to the position vector. So now I'm just going to write it as such. So the position vector would have the x component of cosine t and the y component of sine t. And so there we have our position vector. Next, for the velocity vector, well, the velocity vector I said is equal to dx dt, comma, dy dt. So dx dt is really just the derivative of the x component of position. And so the derivative of cosine is negative sine of t. And the y component of velocity is dy dt, and so that is just really the derivative of the y component of position. And the derivative of sine of t is equal to cosine of t. And now, finally, for acceleration, for that, well, it also has two components, and each component essentially is the derivative of the respective components of velocity. So for the x component of acceleration, we would derive negative sine t, and the derivative of negative sine t would be negative cosine of t. And then for the y component of acceleration, we would derive the y component of velocity, and the derivative of cosine of t is negative sine of t. So the acceleration vector would be negative cosine t, comma, negative sine t. So at this point, I'm going to have to end this video, but please look for another video that will finish off this problem and all the things that you have to be able to do with two-dimensional motion. And thank you for in particular watching this one.